Thank you all for coming today for this IRC, Irish Research Council Scholarship Information Session. All right. My name is Hongzhou Zhang. You already know him. All right. So we have several academics from the School of Physics presenting today. Okay. So what will happen today is I will talk about briefly, give you an overview of the postgraduate PhD education at school here. And then I'll talk about the IRC application, and followed by the interesting part, the projects from our academics. All right. So after each talk, you can ask one or two questions. All right, but please keep your questions short. And then after the all the videos or talks finished, you can stay here and asking questions. All right. I'm sure someone will stay at the end to answer your questions. All right. Okay. So now let me start with an overview about the school, the postgraduate students. We are growing in numbers. So we have 120 students, PhDs so far. Okay, you can see about 1/4 is supported by this IRC scholarship. We also value equality, diversity, and inclusion. Okay, so that means you see we increase the female students. It's almost a 1/4 as well. And also we have a lot of non-EU students joining us at the moment. Most importantly, our academics works in very diverse fields, okay? So I probably should do something here to remove this. Okay, so you see we have 8 leading researchers in astrophysics and space sciences. We have 2 working on the magnetism, all right? And it's not very strict classification, but we have 3 in nanobio and soft matter. We have 5 in photonics, 7 in nanotechnology, and quite a lot in theory, okay, computational work. All right, I can assure you, all of us are leading researchers in the field. Otherwise, we won't be here. Okay. All right. So now a very brief overview about the PhD, what will happen. Okay. First of all, if you want a PhD degree, you must make original contributions to knowledge. So that is the criteria for your PhD examination. All right. So to get there, you need to do 4 years research. Of course, we are offering some talk modules to strengthen your background. And also you got opportunities to start your teaching. That will be paid. Okay. And then this School of Physics and Current has lots of cutting edge research facilities. For example, the Advanced Microscopy Laboratory that hosts a lot of very expensive the instruments that allows you to see atoms or even play with them. Okay, so then we have this high performance computing facility that allows you to explore some theories about condensed matter or about universe. Okay, so you will not be work alone. You will be supported by several academics. Your supervisor is leading the thesis committee. You will be also supported by a non-supervisory committee member who is a researcher working in the similar field and who will give you advice, okay? And your thesis or your journey will be monitored by examiners, right? So that's the support from the school in terms of academic progress. And then the school and college provide a whole lot of other supports, like admin supports to deal with finance or your registration. Okay, so if you have issues, college has constantly support. Okay, so relevant to today's seminar or talk, most importantly, you will be paid if you successfully get this IRC funding. Okay, so by IRC, they will pay you stipend 18,500 per year. Okay, so I'm sure lots of academics here, we have personal individual grants. Okay, so you might have support from the researchers themselves as well, same amount of stipend. And also the tuition fees will be all covered by either IRC or your supervisor. Okay, so that's an overview of the PhD. And regarding the IRC application, the first important thing is the eligibility. You must get a first class or top 2-1. Okay, so I know most of you haven't finished your undergraduate degree yet. So what IRC will do is it will give you a provisional offer, okay, contingent on you get this mark. Okay, and then you cannot have 2 unsuccessful applications in the past, all right, and then you cannot be a current holder of IRC. So these are the eligibility, okay? So in terms of the timelines, you are the applicant, okay, not your supervisor or not the school, because IRC treated you as independent researcher, so they deal with you directly. So you must submit your application by the 20th of October. Okay, it's only 2 weeks to go, so not much time left. So we need to act immediately. All right, and then by the end of next March, you will know if you get it. All right, if you get it, you need to talk to your supervisor, and then we will nominate you for the school, for the college. So you go through the admission process. You will start your PhD on the 1st of September next year. Of course, after 4 years, you get your PhD and you will be doing your own research. All right, so how to apply? Basically, as we already discussed, you must secure academic to support your research or project. All right, so talk to someone whose research interests you immediately, and they will help you to develop the project. Right? And then you can only create one application, online application. All right, so basically you need to fill the forms that includes your CV, personal statement, and career plan, and this project. It should be written by you, of course, with the support of your academics. All right, so then the suggestion is you must submit your application 6 hours before the deadline. The reason is traffic, always traffic. All right, if you submit at the end, they won't guarantee your application will be submitted or accepted properly. Okay, so the last piece of task you need to do is after your submission, you must remind your supervisor to submit their part by this date. All right, that's your responsibility. Make sure they do their work. All right, so any questions for this part so far? Hi. That you are doing.
Should we mention the fee structure that Trinity has and how that depends on the residency in the previous 3 years?
The fees.
The fee structure that Trinity has for EU and non-EU students, because there's a cap on by the IRC, right?
Yes, yes. The IRC doesn't distinguish the. Oh, it does. Sorry. So let me. Very good question, Felix. I forgot to mention the successful rate, right? So you see, this is 18% successful candidate for our regime, right? So this is for EU students, all right? And this, another category is for non-EU students, very much competitive. I need to mention this as well. For physics, for our applicants, the successful rate is 40%, much higher than this. All right. So to answer your question, Alex, no, IRC won't offer.
This is the residency requirement, right? So if anyone who's doing an undergrad gets automatically in the EU category after 3 years.
Yeah.
But someone who's not lived here for 3 years by next September would have to somehow cover the fees, the difference.
Yes.
10,000 or so a year, right?
Yes. We can talk about the non-EU fees in another meeting.
Yeah, I just wanted to mention this because I know there's some interest among the quantum MSc, among students who just arrived, to whom this doesn't automatically apply, like for undergrads.
But I would encourage everyone, including non-EUs, to apply. So because IRC does give awards to excellent applicants. All right, so we can deal with the non-EU fees later. All right. All right. Thanks, Alex. Any more questions for me? Okay, very good. Now I'll hand over to Professor Jones.
I have the honor of going first. Afternoon, everybody. Some of you know me already. Lewis Jones, I've taught you in the nano labs. My group has an overarching drive of trying to teach old microscopes new tricks. I won't comment on why Trinity owns many old microscopes, but there's still a lot of space in this area. My email is there, and I'm quite easy to find on the internet, right? So some of you may have seen one of these machines if you've had like the CRAN days in the nano labs, or an internship, or finally a project down at the AML. This is one of the electron microscopes we have down there. Exactly what it is doesn't matter too much. But these machines, they form a beam of electrons. The beam of electrons is of the order of 80 picometers wide. That's sharp enough that when it's scanned across the view, the beam is narrower than the gaps between atoms, and we can form these atomic resolution images. So that's an experimental image of atomic resolution of a single crystal of silicon. There's the Ball model to prove it. That's a very simplistic drawing. This is where we are. So this is campus. I don't know how many of you have been down here. This map can be provided on request. That's our building. We're in here. That's the current team from the summer, and there's now 3 new PhDs since that was taken. And this is our sort of strapline, right? So in the ultramicroscopy group, we mostly look at small, modular, retrofittable technologies, either in software or hardware, depending on what we we're good at, to expand the performance, functionality, or lifetime sustainability of electron microscopes, okay? And if a research project doesn't meet that brief, we don't do it. So everything that's happening in the group has to fulfill that criteria. You as IRC potential applicants have to come up with the research project. Now, full disclosure, the professors often have a biased interest and might guide you towards a certain idea, but this is how we triage ideas and come up with what we're going to work on in the group, right? So that is what an electron microscope is to a modeling computational group, of which there are excellent ones, okay? A real microscope, this is already a heavily simplified diagram of a slightly more realistic one. And basically the differences between what a simulation researcher thinks a microscope is made like and an actual microscope is made like. The differences is where we find the interesting areas for researching the cracks, right? So at the moment in our team, there are different people working on all of these areas that exist in a real microscope that the simulation people just forget about. Speaking of which, hello, Stefano. So in a real microscope, we have to worry about the train going past. In a real microscope, we have to worry about the data rate, the speed of cameras, the response time of scintillators, and all these sorts of things. And so there's a lot of challenges. These things shown in orange is where there's people in the group already working on it. And this sort of 4 years going forward, where an IRC person might fit nicely. We're very interested at the moment about scan distortion, scan hysteresis from electromagnetic disturbances in the lab, making the microscope more robust against the environment, and also new designs of camera technologies. So trying to repurpose things like medical cameras into the electron world to make them an order of magnitude cheaper for the end user. Oh, that's me. I'll get the end of it. That's the end of my slide. I'm going to stay around to the end if people have questions. If you're pretty handy with building things, you'd find yourself at home in our group. If you prefer more computational stuff, we do a lot of simulation as well. we're also starting a company to commercialize some of these parts of the equipment. So if you're interested in that sort of entrepreneurial space as well, we might have interesting things to talk about. Thank you. Sorry. I'm happy to take questions. And also, I mean, two of my senior soft students are there. If you want to get the dirty gossip, ask those chaps what it's like to actually work in my team. But I'm very happy to take questions.
Maybe later.
Yes, maybe later.
Okay, hello. So I'm Professor Cormac McGuinness. And so I'm going to talk about two different projects that I would love to be able to recruit students to in my group. That's investigations of bimetallic catalysis reactions and the on-surface synthesis of one-dimensional and two-dimensional nanostructures and nanomeshes for the purposes of sensors. So what kind of research am I involved in? In particular, I'm involved in surfaces and the spectroscopy of surfaces and the electronic structure of the materials on surfaces and at interfaces. And so in particular, one of the things that I do in addition to the in situ laboratory-based X-ray spectroscopy that we would do here on campus, I end up using tools, or my group uses tools at international synchrotron radiation facilities, such as this one picture here in Lund in Sweden, just across the bridge from Copenhagen and Denmark. And so this is a photo of the instruments that we could use at that beamline at that X-ray radiation facility at Max 4. So the two potential projects, which I'll describe in the next two slides. The first is a study of bimetallic catalysis, and in particular the influence of ruthenium for efficient lower temperature operation of the reduction oxidation reactions that would occur in solid oxide fuel cells. So that will be studied through thin film deposition, surface science, X-ray spectroscopy techniques both here and at the synchrotron. And then the second project is an on-surface synthesized functional porphyrin one-dimensional and two-dimensional nanostructures and nanomeshes, their electronic behavior, their electronic structure, how we assemble them, and then how then potentially we transfer them onto devices or surfaces that can be used to integrate them into devices and to develop sensor prototypes. So for the first project, ruthenium turns out to be an exceptional material, exceptional elemental material when involved in binary and ternary compounds. And so one of the key things, its electronic structure tends to modify the electronic structure of all of the surrounding elements in the material it's in. And so we've observed this, the magnetism group are pursuing a range of materials based on ruthenium, but in this case, I'd like to pursue the study of oxide materials on ruthenium surfaces or ruthenium metallic alloys, where in particular the oxides then are allowed to be reduced at lower temperatures than they would normally otherwise be. So this would be through in situ thin film deposition, and we would use a new facility in Cran, which has been open for 2 years, which uses both RF sputter deposition systems and ND sputter depositions, as well as X-ray photovision spectroscopy. So we would use thin films which we have developed there and measure there and prepare in situ there, and then evaluate the action of forming oxides on these, and then the reduction of these oxides in differing atmospheres. So there's a photo of the facility in Cran, but then we will also then be doing experiments on single crystal surfaces in the other photovision facility in Cran. So some of the information that we get, we'll be looking at elemental materials, the elemental core levels through XPS, and then we'll be going to facilities such as the one I showed you at BESS in Sweden, or this is the BESSy synchrotron in Berlin, where we do X-ray absorption spectroscopy of these materials. And this would be in combination with Professor David Payne at Imperial College London, where we'll do some in situ ambient pressure XPS studies. So a whole range of different spectroscopy will allow us to look at these interfaces and buried interfaces, and potentially then allow us to go to test these in a solid oxide fuel cell. So the second project is what's called on-surface synthesis, and it makes use of something which you might describe as the surface analog of click chemistry. Click chemistry was awarded essentially the Nobel Prize in Chemistry just 2 days ago, but this is since 2001, or maybe, sorry, since really 2007, 2D and 1D on-surface synthesis has developed, whereby you put molecules on the surface. In this case, we're putting what are called porphyrin molecules on the surface. You may not know porphyrins, but iron porphyrin is part of the heme molecule in your blood. Magnesium porphyrin is part of chlorophyll. Okay, so these are functionally active molecules, and if you put them on the surface in this way, where they've got bromine as part of them, you can heat them up. They form chains this way because we've got a dibrominated chain, and then we can cyclodehydrogenate and make additional changes to the electronic structure. And so we can look at this with STMs, look at the molecules on the surface, we can look at the chains, we can look at the ribbons that we form in this case. And again, we can use X-ray photoemission spectroscopy to look at this in detail. So the objective is to then study these one-dimensional, two-dimensional meshes, including porphyrins, which are going to be produced for us by Matthias Senge in terms of the precursor materials in the School of Chemistry. And then we're going to examine how we can get them to behave on the surface. And so potentially the idea might be to incorporate these into field effect transistors. Imagine, this is some of our results where we have an individual porphyrin incorporated into a graphene nanoribbon. And while we haven't yet made this kind of device, other groups are making similar sorts of devices. So our idea is to engage porphyrins and their functionality to potentially use them as sensors and then detect sensitively the volatile organic compounds that can interact with these thin film devices. Okay, thank you very much.
Any questions? No? Thanks, Conrad.
Great. Evening, everyone. So I'm working on organic optoelectronic materials. So that's materials for photovoltaics or for light emitting devices. So the stuff in this slide is light emitting devices. And we have a project on all organic LEDs. And at the moment, if you want to make a blue emitter, those systems have got heavy elements like iridium and rhodium in them. Another good example of a light emitter is the lead perovskites. Okay, so those are expensive and environmentally damaging. So we want to move to all organic systems, and in particular, they're needed in the blue. So we need longer lifetimes, more efficient, and the project we're working on at the moment is so-called thermally activated delayed fluorescence OLEDs. I'll explain what that is in the next slide. And one of the things that we're focusing on at the minute are so-called charge transfer states. That's where in an excitation, an electron is transferred, say, from a donor to acceptor, or from one part of the molecule to another. Okay, so if you have a light emitting device, they're doing electroluminescence. You put holes in one electrode, electrons in the other, they'll meet in the middle, hopefully recombine and emit light. Now, the thing is, if you have an electron and a hole in the system, they have spins, and there are 3 times as many ways that they can form a triplet spin state as a singlet. And as you probably know, only the singlet will fluoresce. The triplets emit light only very weakly and slowly through a process called phosphorescence. And in the absence of spin-off coupling, there would be no emission. And it's only, in all carbon systems, it's only via weak spin-orbit coupling that happens. So the reason for putting things like rhodium and iridium and so on in there is they're high Z elements with large spin-orbit coupling, so they make this process more efficient. Now, what is this TADF mechanism? Well, here's an energy level diagram. We have both local excitons and these charge transfer excitons, and we have singlets and triplets in both types. So a local exciton, we have a big molecule which has got a donor part and an acceptor part, which are weakly interacting. A local exciton might be just on the donor part. Whereas a charge transfer exciton, the hole will be on the donor, the electron will be on the acceptor. And the thing is there, because the electron and hole are weakly interacting, the splitting between the singlet and the triplet in that case is very small. So what can happen is form all these triplets, but because in this case the splitting is small, whereas it's large for the local exciton, you can undergo a reverse intersystem crossing and harvest the energy from your triplets in that way. Okay, and so that's the project at the moment. The methods that we use, many body quantum mechanics. So the language there is Green's functions, Feynman diagrams. The methods that we use are called the Bethe-Salpeter equation. This is the Feynman diagram for the Bethe-Salpeter equation, and also time-dependent Hartree clock, which is similar. So we have all these electrons and holes interacting, and electron-hole pairs, decaying, and so on. I do a lot of code development, and if you're interested in getting involved in code development, there's that possibility too. So HPC development in C, with parallel programming through tools like message passing interface and OpenMP. There's a lot of numerical work handling very large matrices. And just to show you, these methods, when applied now to electrons, work extremely well. So this is the dielectric function from Anate's TiO2. Okay, these are all from my own code. The dots are experiment, solid theory, large sodium cluster, and porphyrin. This is a magnesium porphyrin in a bacteria chlorophyll. The solid line here is the experiment, and the red line is the theory. So it works extremely well. Now you can see some of the things that we've been doing. The website here is a bit messed up at the minute because it's just been taken over, but you'll still find the publications there. So there's work on sodium clusters. That particular paper describes the method, so you'll see the theory behind what we're doing, some of the methodology, and some of the results. And the code now is open source, and here in Dermot Green's group in Queens took the code and added positrons to it. There was this article in Nature earlier this year where Dermot's group were able to calculate the binding energies of positrons to small molecules with accuracy as good as experiment for the first time. Okay, so in summary, a bit of chemistry, a bit of physics, a bit of maths, and a bit of computing. Okay, thank you. So I can't stay this evening, but you'll get me there at the end of this.
Okay, hi everyone. My name is Alessandro Lunghi. I'm an assistant professor here in the School of Physics. And this is a simple slide to give you a flavor of what we do in my group. The people which is currently in my team, and we're always looking for the people to join us, of course. In a nutshell, what we do, we try to understand how the spin evolves out of equilibrium in magnetic molecules. So you can think of a molecule as a sort of giant spin. If you have unpaired electrons, it will give rise to a magnetic moment. And it's possible to influence this magnetic moment externally with microwave pulses, for instance. And technological applications of magnetic molecules are in different fields. For instance, one can think of them as a sort of very tiny version of a magnetic domain like you have in hard drives. So one could think of using them as a high density information storage device. or they could be used as a sort of qubits, spin qubits in this case. So spin has a quantum property, so you can manipulate it, observe radial oscillation and coherence in these kind of systems. Most of the time, we think of molecules like a sort of object just there in space. But actually, what we try to do, we also try to understand how the environment of magnetic molecule influences their property. So we're also looking at devices. I should have said it from the very beginning, we are theorists. So we use a combination of electronic structure theory, high performance computing and theory to study these systems here. And this is sort of the loop that we use to study systems. So usually we start from developing some level of theory. This is usually based on open quantum system theory. And then we try to couple that with simulation, so something like quantum chemistry. And quantum chemistry essentially can give you the properties of a real material just by knowing the position of the atoms and the number of electrons you have. When you put these things together, so the formal theory of quantum mechanics and quantum chemistry, you can actually get a quantitative picture of what's going on in the real system. And in this case, you see the relaxation time of spin, so the time it takes to spin those its quantum properties as function of the temperature. And you see here the black line is the experiment, and our simulation can describe this process quantitatively across different regimes as function of the temperature. Another area that we're interested in is to couple both machinery here with machinery as well. And the reason is that quantum chemistry is usually very heavy. So we need very large computational facilities to carry out these calculations. And then it can take several months, if not years. Machine learning could speed up this process. So the idea is to interpolate between different quantum mechanical calculations and increase the throughput of our simulations. And if everything works, at the end, you can think of the material design in the first place. So you're not just describing the theory, but you can actually predict the properties of a large pool of different materials and see whether it's possible to select something which is useful for the actual technology. So we would accept in principle any proposal from you guys which is within the remit of what I just described. I also have something in mind myself, which I could propose if you like to jump on it. Very recently, people have published in Science these results where they show that you can use optical, let's say laser, optical excitations to control the spin of molecules. This is a big breakthrough because it means that we will be able to address single molecules one at a time, meaning that you could place your molecule near to another object, a quantum object, and use the spin as a quantum sensor at the level of the single atoms. There is no, however, understanding of how this process exactly works. And the idea for this project would be to start developing a theoretical framework to describe these processes here that people observe in the lab. And again, more or less, the pipeline I was showing before could be applied to this project here. So this would be a combination of electronic structure theory, quantum chemistry, machine learning, and theory. Okay, so you can't read it here, but what I was trying to say that there is some level of flexibility to suit, let's say, the inclinations of the applicant. So there is both numerical and theoretical work, and depending whether you're more inclined towards one or the other aspects, we can try to treat the proposal. Right, so that's everything from my side. You can reach me by email or stop me later if you have questions. Unless you have questions now, of course. Thanks. Thank you.
All right, so my name is Professor Luke Matra. I'm a new assistant professor in physics since January, and I lead a growing group of currently 4 PhD students. So if there was a sentence to describe the project that I would be willing to offer through this IRC program, it would be observing the aftermath of splashing planets with cutting-edge observatories such as the Atacama Large Millimeter Array, which is at 5,000 meters in the Atacama Desert in Chile. So smashing planets, why is that interesting? Well, because we think terrestrial planet formation, so the formation of planets like on Earth in the final stages, happens through giant impacts. And there's plenty of evidence for these giant planetary impacts at home, meaning in the solar system. There's Mercury's higher in content, the Earth-Moon system, so our own moon, we think, came from a giant impact, the Mars hemispheric dichotomy, the fact that the Uranus is tilted, as you might know, compared to the plane of the solar system, and high angular momentum in the Pluto-Charon system. Does this work? Oh, it works. So giant impacts were thought to be common in the early solar system and are likely common in extrasolar planetary systems. They are highly disruptive events, as you can see in these SPH simulation, and strongly affect basically the final configuration of extrasolar planetary systems, but also they affect the size and the composition and the final composition of forming terrestrial planets. Now, interestingly, recent simulations have started to look at the effect of these impacts on the atmospheres of these planets. For example, these simulations show basically, depending on the impact parameter and various other parameters, how much of the atmosphere of the original two colliding planets gets removed. And so we think that some gas is being removed, as well as the rocky material in these terrestrial planets in the early stages of formation. So how do we look for giant impacts in extrasolar planetary systems? So we look for them by looking for large amounts of dust. And you can see on the left, there's like a spectrum of a planetary system. You've got the star on the left with the black body-like function. And then on the right, you see that there's a bump, a so-called infrared excess, which represents the presence of large amounts of dust at a few AU by looking at the temperature. So through Wien's law, the peak of this curve in this planetary system. This planetary system is very young compared to the solar system. It's only 23 million years old, and it's quite nearby at 28 parsecs. And so there's a lot of dust. So 3% of systems between 10 and 100 million years old show this bright warm dust and a figure U. And our theories say that you should have a lot of collisions early in this kind of time range. But we can't observe the planets directly because they're too small. So we probe the aftermath through this dust emission. So we look for unexpectedly high warm dust levels. We look for extremely overabundance of micron-sized grains. And we look for spectral features in the solids. For example, silica-rich composition, which is indicative of high velocity impacts that raise the temperature sufficiently to create these compounds. But something that I've been more interested in recently was the surprising detection of gas emission from one of these systems with a lot of dust that we think comes from a giant impact. And the presence of gas, particularly CO gas emission, basically indicates that gas was released as well as dust in this impact. And this is the very first ever detection of gas from a giant impact in an extrasolar planetary system. And it tells us that we might be able to start detecting the release of atmospheres that happen in the aftermath of these impacts. And to give you an idea, the amount of CO mass that we can detect with our telescopes like ALMA nowadays is only 9 to 23% the CO2 content in Venus's atmosphere. So this is really reasonable, and it really shows that we can now start doing this going forward. So the idea of the PhD project would be to basically follow up on this system where we just detected CO gas to look for the first time ever at basically the composition of gas from a strict atmosphere and an impact, and to try to back out basically the sizes of the planets that would have collided and the time that has gone past since the impact. And we do this through high resolution ALMA observations, such as shown here. What I'm showing here is actually some simulations of some ALMA observations that we got time for. So we've got data coming for this project in spring of next year. So just in time to start your PhD in September 2023. And then the idea is to expand this to other systems. So to search for gas in other systems with evidence for large amounts of dust. So to answer the question, how common are these atmospheric stripping impacts? And also one potential idea is to model the chemical evolution of the gas after impact. So yeah, if you're interested, stop me at the end of this or send me an email by tomorrow or as soon as possible so that we can move forward because the timeline is very short. All right, thanks very much.
I don't know photos. Is that?
No, it's the other direction.
The other direction.
Yeah, again.
Ah, okay. Okay, so let me close this lovely Italian moment here with the last of Italian group here. So I'm Stefano Salvito. I'm running the computational spintronics group. So It is a relatively large group, about 20, 25 people, depending on how you count, and different time of year. And essentially what we do is we model material and we design new material. So what we want to go to the computer, do in silico experiment, and provide a suggestion for new material to be made that hopefully targets some specific application you want. Okay. Now, how do we do that? Quantum mechanics has given out a range of numerical techniques, and here what I do in very, very sketchy way, I just putting them against time and length scale. Okay. So if you have if you're looking at something that happened very, very fast and that does not involve a gigantic number of atoms, you're down here, and this is the realm of quantum mechanics and quantum chemistry method. This is the one that Alessandro, for instance, mentioned. The problem of those methods, which are extremely accurate, okay, but we're really talking about few tenths, maybe hundreds of femtoseconds, okay. Am I muted again? No, that's okay. Oops. Okay. So actually, you use this extremely large range of technique. Okay, and a lot of the technique essentially consists in understanding how you represent things, how you represent the electrons, how you represent the atoms, and so on, and actually how you implement this method. And the problem are quite. I mean, varies quite a bit. So, we will work on a full range. A lot of stuff is related to magnetism and magnetic material, but not only. So we think about how you can design, for instance, 2D structures, how you can design objects for solar harvesting, for thermoelectricity and so on. So in reality, a lot of the thing we do is materials agnostic, so the same technique can be used for doing different things. So I guess I'll finish here, and if you have any question, just pick me up or send me an email or anything. Thanks. Cool.
Good evening, everyone. So you know me from last year. I taught you can dance metaphysics course. I'm Igor Shvets, and I'm a PI in the group what we call Applied Physics Research Group, APRG. It's a sizable research group. We always had maybe 15 people, sometimes more, sometimes a bit less. Reasonably well resourced, and it's quite heavy on instrumentation. We use quite a lot of stainless steel chambers for deposition, measurements, low temperature measurements, and so on. Some of the results you can see here. So this is result on that wall. So this is result from our STM measurements at low temperature. This is the image of C60 deposited on molybdenum oxide template. So the last one here. So maybe I'll just say, a couple of words about what people do after the graduation. Obviously, a fraction of people who can multiply and divide go into financials and banking. The skill is much in demand, analytical skills. But some of my graduates go also into the areas of kind of high-tech instrumentation developments. For example, one person recently went into the ML. This is the leader company in Holland developing the lithography instrumentation for companies like Intel and so on. So they apply from this company. I have a specialization of the group is thin films and interfaces, designing thin films and interfaces to tune their magnetic, electronic, and to some extent optical properties. And I could think of two projects for this IRC call. One of them is antiferromagnetic spintronics. So the spintronics involves ferromagnetic layers. However, there is a substantial class of other materials, antiferromagnets. And if you are to replace a ferromagnet by an antiferromagnet, it offers a massive advantage. Antiferromagnet does not create a stray field. And that means that you can, in theory, change the magnetic moment in the antiferromagnets or the antiferromagnetic vector much faster because there is no penalty associated with moving the stray field. So this is the antiferromagnetic spintronics, and we have done extensive work on this is the record-holding material that has the highest Néel temperature. The Néel temperature is well above the melting temperature, so that's why that means you cannot cross the Néel temperature. You only predict what it is on the basis of some indirect measurements. So this is manganese 2 gold. So we grow epitaxial layers of this material, and the expectation now, the plan is to use these materials for spin valves involved in antiferromagnetic materials and also for spin torque experiments. So this is one project. The other project is transitions between insulating oxides and conduction oxides. So this is vanadium oxide. It's a whole zoo of different vanadium oxides, and they all, in principle, most of them would have metal to insulated transition. And that particular one would have VO2, would have metal to insulated transition very close to room temperature. And now the materials that can, where you can experience metal to insulated transition can be used for memory storage. So this is the other project. So that perhaps I would stop at this stage, and if you have any questions, you can find me in the Fitzgerald building. My office is on the ground.
All right, everyone. Nice to meet you. Chef and Senses, apologies, couldn't make it this evening. I'm his PhD student, John Reinprestel, and maybe I'm pretty well positioned to talk to you because 4 years ago I was sitting where you were listening to Stefan give his talk about why I should join the Foams and Complex Systems group. this group is fantastic to work in. We're at the intersection of theoretical, computational, and experimental work. You can see examples of our work on the slide and even on the image up there in X-ray foam. And the project that Stefan is kind of offering at the moment is about these foam structures and how they appear in biological structures. So here in the first image on the left, we have an example of a fairy liquid foam, simply made with fairy liquid and water, that's being emitted from a pipe. This kind of unconfined foam then can be modeled in with a computer simulation. We use both existing computer software such as Surface Evolver, but you also have the advantage or the opportunity in the group, as I'm doing at the moment, to develop our own software from scratch using either Python, C, or Mathematica sometimes. And these structures are reflected in nature. So you see these plants and the structure of this brown native paper wasp nest. The other kind of project related to this field is in these 3D tissue packings of curved epithelia. So these epithelial cells, which develop on curved surfaces, these foam structures develop unusual shapes. A few years ago, the New York Times said it was the most exciting discovery of this before-seen shape, the scutoid. And recently, we've been able to replicate these in experiments in the labs, and also produce them in Surface Evolver and other softwares. The last one then is about these columnar packings of bubbles, which can be also seen, similar structures can also be seen in the development of the notochord of certain fish species. And yes, so the development of these columnar packings and their classification, again, like I said, another kind of blend between experimental work, computational work, and theoretical work. As for what my experience as a PhD student has been like in the group, Stefan is an excellent supervisor. It's very easy to schedule meetings with. The group is quite small and close-knit. So if you're interested in having a supervisor who you can contact easily and who is very hands-on and very interested in the theoretical work and computational work, he's a great supervisor to have. So I'll be around with the others if you have any questions about the work in the group or specifics, or if you have any questions of what the day-to-day work of being a PhD student is like in the School of Physics, let me know. Thanks so much.
Our PhD students to come and give these talks actually, because we get it from the cold, right? Yeah. Okay, so most of you who have been in Trinity for your undergrad will know me. I'm Louise Bradley, and my area of research, which you may not know, is nanophotonics. So I'm going to just tell you a little bit about the project that I'm offering, and in fact, I have the funding for this project already. So if anyone is interested, but if you're interested in the general photonics area or other areas that we work in the group, come and talk to me as well about the IRC. So just to briefly let you know, one of the areas that we're working in is on dielectric nanostructures. And dielectric nanostructures offer you the possibility to manipulate light in very exotic ways. So one example that I'm just going to show you is how we've used these silicon squares here. So you make a metasurface of them. Each of them is acting as a scatterer of light, a Huygens scattering source. And because they're dielectric, you get magnetic and electric dipoles. You get the quadrupoles as well for both. And the way that they scatter then, depending on the amplitude and the phase, they'll interact and interfere destructively or constructively. And so, for example, for this surface, when you shine light through it, you get no change in the, so this is if you have nothing there. And here is the electric field when you have your metasurface there. And you can see that your electric field is completely unperturbed. So it's as if it's not there. So you get an invisibility of the surface. And that's because all the scattering, which contributes to your reflection in the backward direction and to your transmission in the forward direction, from these different multipolar orders is interfering, and you don't get anything in the forward or backward direction, you only get scattering in the transverse direction. So that's one of the ways in which people talk about an exotic use of metasurfaces. And Igor mentioned earlier, for example, with vanadium dioxide, we've done work where we use the same kind of control of the scattering antenna to be able to get anomalous reflection and to be able to tune it so that you can get reflection. Your light is incident in one direction, even normally, but the reflection can be tuned over a wide angle of reflectance angles for a single angle of incidence. And that's due to the constructive and destructive interference of the light that's being scattered from the antenna on the surface. So what's interesting though is even though you don't modify your field, you get a really high enhancement of the electric field inside the dielectric structure. So you can think about how you can interact with this. So briefly, one of the examples that we did to try and see how it worked is we said, well, how do we increase, for example, the emission from monolayer molybdenum disulfide? It's only 0.8 nanometers thick, so you get very little absorption when light is passing through it. So you struggle to make a really good light emitter out of it for devices, even though it can have high quantum efficiency, meaning that for every photon you get in, you get a good number out. The problem is getting many in. Okay, so what we showed is that you can enhance the amount of absorbance in the molybdenum disulfide sitting on the disk. So now we know we can interact with nano emitters, but the next part of the problem that we want to tackle is you can see that this is my molybdenum disulfide. Here is the enhanced electric field, and that's giving us the increased absorbance. But the red there is where all the real enhancement is going on, but it's totally inaccessible in this kind of structure. So that's led us to this project, which is that we're looking at slotted cavity gap dielectric nanostructures. So we want to keep all the advantage of having all the higher order multipoles able to interact with each other. We want to be able to get regions of really high field enhancement. So here you can see we have a factor of 500. So this is a nanodisk with a slot through the middle. And also you can see that we've got very low losses, but you've got a really, really narrow line width giving you a really high Q factor. So these structures are extremely interesting for being able to create nanoscale lasers or for being able to create single photon emitting sources. And so we want to be able to couple these with 2D materials and also with quantum dots to create nanoscale light emitting devices for things, all kinds of things, but basically you require less material, lower footprint, and they're also of interest for different kinds of quantum information systems, particularly the single photon emitters. So that's what the project is about. In the group, we do numerical simulations, fabrication, and all the optical testing and of the structures that we make. And in this case, that will include testing for lasing and single photon emission. So as I said, at the moment, we have full funding for an EU student for something in this area, but we're also have other people working on different aspects of these structures. They're massively applicable across an entire field of biophotonics, as well as for different kinds of optoelectronics and integrated photonics. So if anyone's interested, you can email me at louise.bradley@tcd.ie, or you can look up the group there and see about some of the other things that we do, because we have a number of different research areas that we're working on. Okay.
We have two videos, okay?
Hi, nice to be here. I'm sorry I couldn't be here in person. I'm Paul Eastham. I'm the Associate Professor in Physics, and I run the Quantum Light and Matter group. And as you might guess from me sending a video along to you, we're looking for new PhD students to start in September, maybe through applications to the IRC. So the main things to notice, you can see on the PowerPoint here, the web address of my web group page, my group web page, excuse me, and my email address. And if you're interested in the sort of things we do, I'd encourage you to drop me a line and we can chat some more. So you can see a picture of the group there. That's quite an old photo. We're quite a small group. We got bigger, maybe up to 5 PhD students. We've got a bit smaller again. We're now down to 2. And we're looking to grow again. And what we do really is theory. We make models, mathematical models, analytical as well as computational, to try and understand the quantum mechanical behavior of light, photons, when it's interacting with matter. So this can be things like the motion of electrons in a semiconductor nanostructure, or currents in a superconducting device, or something like this. We have lots of opportunities for interesting projects, whether you're interested in kind of analytical work or computational work. We're mostly kind of analytical with a bespoke bit of computation, but typically we can kind of work with whatever people want. The other thing I guess to mention about our group is, although we're theorists, we're quite closely coupled to experiments, so there's opportunities to kind of really get your kind of teeth into some understanding some problem that maybe ultimately somebody will actually kind of end up looking at in the laboratory. And I guess one other thing to say, because I guess there's a lot of mix of people here, although we're theoretical physicists, I don't think you need to have a theoretical physics degree to start doing a theoretical physics PhD. I have a physics degree and I'm a theoretical physicist. So that's the sort of thing we do. Let me just tell you a little bit about one area I'm quite excited about, which we're growing in the group at the moment. And this is the idea of inverse design of quantum processes. So you may have heard of the idea of a quantum computer. It's a machine which encodes information in the state of simple quantum mechanical systems called qubits. And if you want to do anything with a qubit, which might be some kind of defect in a solid or superconducting circuit or something like that, you need to do a couple of things. You need to be able to prepare it in a particular state. That's called state preparation or qubit reset. And you also need to be able to read out its state. And typically what you would do is you put the qubit in some particular state. You either do operations with it if you're interested in information processing, or maybe you let it interact in contact with some environment if you're interested in sensing, and then you read out the state at the end. So quantum sensing, for example, what you do is you prepare it, you let it evolve kind of in the interactions with the thing you're trying to measure, and you read it out. And of course it changes state due to what's going on. So that's how you measure something using a quantum mechanical system. Now, we have all sorts of processes that we understand for doing the state preparation, the reset, what happens in the middle, and the readout. And particular processes for particular proposed ways of using quantum computers. So again, I'm talking about quantum sensing here. So in quantum sensing, we would put all those together, and I might call that a quantum sensing protocol. And typically that means some sequence of laser pulses or some sequence of electromagnetic fields that you use to control this quantum system. Now, all these processes have so far been invented using what you might call a conventional forwards design approach. So somebody thinks about how its system works. You maybe build a model, you try and simulate it or analyze it, see if it does what you think it does, and maybe you use those results to kind of tweak your idea and improve what happens. And what we're starting to do, and this comes because of advances in our kind of ability to make mathematical, theoretical, analytical, and computational models of these problems, is turn that around and do what you might call inverse design. So we set up a model, ultimately in a computer, but rooted very firmly in analytical work. And rather than proposing a design, we say, well, this is what we want to achieve. So in the case of a quantum sensor, we want the readout, the evolution, and the end to be such that we get the maximum information about the thing we want to measure. And then we let the computer go and find out how best to control this quantum system to do that. So this is a huge and exciting possibility, because really it's not constrained, this kind of approach, by kind of your expectations, your understanding. You can kind of really discover new ways to do things, and then you can kind of expand your understanding to say kind of why did that work. And this is something where we're kind of starting to get in touch with a lot of people doing kind of experiments on these systems, so there's definitely directions to take it there. So if that sort of thing or related problems sounds maybe interesting to you, please do get in touch. You can see my email address on the slide. I'm delighted to talk more. Thanks very much.
Any questions?
Hi, everyone. I'm Evan Keane. I'm going to talk to you about a couple of astrophysics project possibilities in my area of research, which is pulsars. All right, so what is a pulsar? Well, when a massive star gets to the end of its life, so a star maybe 10 to 20 times the mass of the sun, and it runs out of nuclear fuel and goes supernova, the core of that star that was still survives, and it can exhibit a phenomenon known as pulsar phenomenon. So it has gained rotational energy from the large star that was, and in the process of the supernova, it is, what's left is a city-sized remnant, so sort of 30 kilometers across. They spin very rapidly, so many times per second, and they're highly magnetized. And rapidly spinning, magnetized, highly conducting spheres can emit copious amounts of radiation across the spectrum. And so if we point a radio telescope at a pulsar like this, you can see it sweeps out a beam of emission, kind of like a lighthouse. The data in your telescope looks like what's here in the bottom, where you see one pulse every rotation of the star. And so we see this kind of clock-like signal coming from pulsars dotted all over the sky. We know about 3,000 of these at the minute in the Milky Way. Now, as this is ultimately fueled by the rotational energy of the star, but of course, as the star spins, it is slowing down, and there is a critical point where the rotational energy is insufficient to power the pulsar emission mechanism, and so there are what's known as the pulsar death line. This is a line in a parameter space that the pulsar crosses, and then it should turn off, and the pulsar signal should just go away. And so the star essentially dies for a second time. However, we have in very recent times been finding a bunch of pulsars that should be dead and not emitting anymore, but they are. And in fact, they're boomingly bright once you look at them in the right way. And we don't know why this is. And so that's the topic of this first project, is to study pulsars like that, pulsars that shouldn't be emitting, but they are, using a telescope in South Africa called Meerkat. This is actually made of 64 14-meter dishes, as shown in the picture there in the bottom right, operating together, as a phased array. This has been working for the last few years, collecting a lot of data. So we have a lot of data in hand, and more is coming in on thousands of, over 1,000 pulsars actually. But the goal of this project is to study these pulsars that should be dead and try to understand why, by understanding their emission, how the geometry of that emission is, and how their magnetospheres are behaving. The second project I wanted to mention is another pulsar one, but it's using Northern Hemisphere telescope array. So I'm operating at lower frequencies. This is the low frequency array, or LOFAR. So this is a European scale array. So there's a map of LOFAR there on the right, and each little dot actually consists of many, many antennas. And in the Netherlands, it's orders of magnitude more, because that's the core of this array. And any subset of those can be used as a telescope, or indeed the entire thing can be combined together to get a European-sized telescope. And we observe with our LOFAR station, which is based in Birr, and we've been doing that for the last few years. And we also operate as part of the wider network. We observe at very low frequencies, which gives us a handle on the numerous weather effects, space weather effects that affect the pulsar signal, so that we can remove those, which is not possible at higher frequencies. which means we can get a good deep, sharp look at what the pulsar signal intrinsically looks like. And this is what the goal of this, or the aim of this second project is to look at, a wide number, a wide span of different types of pulsars that are, at different evolutionary stages, so that we can somehow try to make an evolutionary tracks for pulsars, by studying, the wider population properties using LOFAR. What's been found in the last few years empirically is that pulsars have multiple on states, and in fact they're sort of discrete on states where a pulsar will emit in a particular way and jump to emitting in a different way, which is in a way that's exactly like what you see in a quantum energy level. We don't know why this is the case, but if you want to come work on that, maybe we can figure it out. If you're interested in these projects, or indeed variations of them, drop me a line. My email address is there, and I'll be happy to talk to you about it. Thank you.
Okay, thanks. So we have another presentation. Professor David O'Regan sent in his apology. I might have to send in my apology for not being able to put it there. Let me try. Okay. You know which one would be for the iPad?
Is it? What's coming out of the adapter?
PC.
Yeah, it might be go for laptop.
Okay. Okay, very good. So thanks very much. So that's from Professor O'Regan, and there are two slides. So, he is working in quantum theory computational field. So he has a fully funded PhD position available. All right. I don't know what is this international community conference, right? So the next slide, that's the three products Professor O'Regan offers. All right. I'm not going to read it. Please.
Oh, you're right. It's just email because the Zoom people won't see that.
Oh.
But maybe they can email it.
Oh, sure. We will send the projects later, the video tape, and also the slides. Right? Okay.
Can you add that to the end of the video?
Sure. Yes, very good. So if you have any questions, feel free to send Professor O'Regan an email. Yeah. All right. So now this concludes our session, all the presentations. But I'm open the floor to you guys. If you have questions, feel free to ask. So, but let me check the chat here in case they have questions. Oh, thank you, missing out. I'm taking that module next semester. Yeah, can you not read more? Lip-read. Oh, that's why they are lip-reading, huh? Could you maybe stop the volume from what I was speaking? That is interesting. Those on the call can no longer hear. All right. Oh, that's okay. Any information about the Coleman group? Sure. So if you are interested, please just drop by his office and talk to him. I'm pretty sure he wants new students. Right? So any questions from our audience here? I can see a couple of familiar faces. Right? Come on. So who are you working in astrophysics? All right, astrophysics. Quantum theory. Theoretical physics, that's it. Theoretical physics. Okay. General physics. What are the others doing? Sorry, nanoscience. Perfect, nanoscience. All right, very good. All right, who are interested in photonics? Oh, perfect, very good. Who are more interested in quantum theory? Perfect. Who are interested in nanoelectronics and microscopy?
Who's not sure if they want to do a PhD?
Okay. Yeah, who will definitely stay here with us for a PhD? I do that, right? All right, very good. So any more questions?
You're welcome to ask not just about science, right? You can ask what's it like to do a PhD. You can ask us, because we all did PhDs as well. Right? So you can ask anything. Yeah.
Yeah.
Ask anything you like.
That's okay.
It's all right, but it's like shocking hard.
PhD.
Yeah. Like I've seen it not easy, but like it's a like don't ruin your life, so.
I would say.
Sorry, can you repeat the question here? You are going to come on. Go ahead.
The question was, is a PhD shocking hard?
Good. So who can answer this, please? You go ahead.
What I would say is, very likely, it will be the longest duration thing you've ever done, even if you've come from the MSc or whatever, you know, and it'll be a orders of magnitude more than your 9-week project. What that means is you have a lot of time to find your way through it, right? There'll be occasions where there will be an actual deadline, like a paper has to be submitted to a conference for an actual deadline. It normally gets extended no more than twice. But then the rest of the time, you know, you sort of, I don't know, you have the space to intellectually meander through the 4 years, right? So what I often encourage students to do is have a few things on the boil at the same time. You know, have an experiment, something simulation-y or computer-y, something reading, and something writing. And you know, you might come in on any day, and one of those 4 things might excite you. The other 3 might sound like death. And then another day, oh, I can't do computer stuff today. I'm going to go read a book. But it's okay because you have the time to switch between parallel streams. You keep these things going concurrently, right? It should be hard. It should be something that by the end, you know, you're proud of for the rest of your life. But I would like to think Trinity Physics has some of the best supports you're going to find to go through that hard process.
Put it in the brain. I mean, if it isn't hard, it won't be challenging enough. It will be boring, right? It's a very good question. Okay.
Benefit and added that it's 4 years, like the other countries have wrapped up in 3 years of coming myself. That's the real benefit.
There's a big difference between 2.5 and 4 years.
Let me see if we still have some audience.
If you go put the mouse all the way to the top.
Okay. So there's still 5 audience there. So Felix,
If you have an embarrassing question, say that one of your friends gave it to you to ask on their behalf.
how do you find your final year project, research project? So far, have you been enjoying it? Okay. What are you working with? Don't answer. All right. Any questions? Yeah. Oh,
On the IRC website this year, they have no mention of referees for PhD forms. Is that something they've changed, or you know, something there?
Very good question. So the question is, on the IRC website, they didn't mention the referees this year. Is there anything changed with that? Okay. So according to the core documents, I can't find any information regarding the referees. So let's just not to worry about that. Okay.
When your supervisor has to write this manual, basically sort of a reference. That's fine.
Yeah. If you have doubts, send IRC a question. Very good question. Thank you. Please.
And when you're looking to do a PhD and you're not quite sure, is there supposed to be like a clicking moment where you're like, I definitely want to do it, or do you just jump in something you?
Okay, very good question, psychological question. So let's repeat the question, okay? So you are not sure if you want to do the PhD. Is there a click moment you will be sure about doing it? Or the journey will be very long. So eventually when you get a PhD degree, you're still not sure if you should do it. Is that the question? Who is going to take it? Please. Go ahead.
I think it would have been a very exciting time to be a Victorian explorer, where you just wander off, find an island, and then claim it. Or in the astrospace, there are still planets and stuff you can name because they've never been there before. But like in everyday life, there's very little unclaimed space. Right? Maybe if you're artistically inclined or poetic, you could pen some lovely poetry that nobody's ever used those words in that order before or whatever. In a PhD, you have the time and space to have an idea. It might be only one afternoon of one day of one of those 4 years, but you might have an idea that nobody has had that intellectual nugget in their head ever before, out of the however many billions of humans have existed. If you are curious to find what that idea nugget is and be the only person who've ever thought that thought, then a PhD might be right for you. I don't know. Other people might have a different explanation, but that's what it was for me.
I like the answer.
Yeah. Did you prepare?
Yeah, we work together. You usually find worse.
Mark, please.
I might just add something from my own past, dreadful though it was. You know, when I was choosing my PhD, I was choosing between 3 possible groups in terms of a group in chemistry that was developing photovoltaic cells from mesoporous titanium dioxide, so a very new thing at the time. Or I was contemplating doing traditional plasma physics with small plasma devices. Or I was eventually chose to do atomic physics using X-ray spectroscopy and a different sort of laser-produced particles. How did I arrive at the particular decision that I made? I did look at the people who I would be working with, but also what excited me most about these different projects. And I found that, you know, I ended up choosing the project which had, for me, it seemed the potential to go further, you know, and play to my strengths as well. So you got to choose something which, you know, maybe excites you. You can envisage yourself working in beyond PhD, and something that you think you will like to do and plays to your strengths. You know, I think that's the key things that would allow you to make a good choice. Now, whether it's necessarily that click that you're looking for, you know, then, you know, it may be that there are quite a number of PhD students who enter PhDs who don't experience that click when they're choosing the project initially, but then they really come into their own when involved in the research. You know, so I think, you know, the exposure to constant day-to-day, week-to-week, month-to-month research, it can be really invigorating, no matter what the topic, no matter what the project.
So Luca.
Is that something on the chat?
Yeah, so maybe.
Yeah, I was just gonna say quickly, like, in my own experience, like, you just go with something you find you're really interested in. Like, it could be like something to do with your senior soft projects. It could be something that, you know, you've seen videos online. Like, you just go with something that you feel like it's interesting and it's a hot topic as well at the moment. But something that hasn't been mentioned is it's very important to gauge the supervisor as well, because, like, you know, you're going to be working with them for 4 years, so you really need to have a good feel about the supervisor. So that That said, go talk to people like before. Don't just exchange an email. Just go to their office and get a feel for like what the actual person is like as well as the scientist. Because it can go wrong sometimes, but it doesn't in most cases. Not for us, at least. But yeah, just in general. That's a general point. Now in the chat.
How are you doing?
How are you doing?
How are you doing?
I'm doing well. Surviving, enjoying this moment.
If you're unsure if you want to do a PhD or not,
Ethics.
should I go?
We have an audience, we need to talk to this.
If you're unsure if you want to do a PhD or not at this point, right? This would start in a year from now. You'll find yourself in a more comfortable position having applied and having funding to turn down come next year than the other way around, right? So if you're unsure, feel encouraged to apply at this stage, and you can turn these things down from your perspective. I'm not sure if I'm meant to be recommending this, but that's a more comfortable situation to be in.
Absolutely. Right.
So, that's right, just on the point actually, does like turning down an application count as an unsuccessful application? If you only have two, you know,
Can't answer, but let me ask it to the microphone. So if you're turning down award, does it account for unsuccessful application? Anyone can answer?
My suspicion, if you were actually successful, and then it came to be the start date or registration date, many people develop long-term medical conditions very rapidly. I don't think that could be held against you.
So the generous consensus from this room is it won't be counted as unsuccessful application, right? Just to follow up with on the Felix point right here, pragmatic approach for you guys to do is just find a supervisor, submit an application, right? Please. So you are not obliged to accept the award. So it's totally up to you. But I would encourage you to really think about it when you have the award, because it's IRC, it is a personal award. It's on your CV. When you apply for postgraduate, it matters, really matters, right? So for future career, it strengthens your opportunities. So this is really great award to have. All right. So questions?
And there's no other like alternative sources of funding, let's say, other than that, you're goosed.
Is there any security, other funding if we can't get the RC? Yes, go ahead.
So, I mean, as was commented by Professor Bradley earlier, some professors will have got funding to add human resource, like PhDs, to a grant, and they may already have funding. There are other funding networks. One that we have in Trinity, we also have a Center for Doctoral Training. This year, this is between physics, chemistry, and engineering type things. This year, we'll be looking for 6 PhDs in the advanced characterization of materials. I'm biased because I'm the director of that, and that's based down in CRAN and the AML. But that's another PhD center where you just apply to that center. It's more like a structured master's in the first year and then 3 years of research. So it's not like this is the only show in town, but it's, I think, the only show in town where you can have a lot of strength negotiating with the professor what you want to research. You know, most professors have an idea of what they want to do next in their research trajectory. Well, I hope so. But like, if you say, I'm really passionate about such and such a topic, and then find the right person to sponsor you, very rarely will a professor say they're not going to sponsor a good candidate to go in that direction. You know, it's the most flexible.
Great. So some professors have already funded positions. Professor O'Regan said, and I have 3. And this has 2 or 3.
No,
one at the moment. So Felix, you have 1, and Cormac maybe have done CDT. How many for the CDT?
6 this year.
6 for this year. So you can apply for this and also simultaneously apply for CDT, right? So that's a lot, right? So it's good. Okay. So other professors who are not presenting today, it's not because they are not recruiting, it's because we sent the notice quite short, right? So they won't have time to send in their presentation. So if you find some interesting topics from other professors, so feel free to knock their doors, right? Of course, knock my door, please. Any questions?
I would say excellent candidates are more in short supply than money. Right? So you are the valuable commodity in this equation.
But don't worry if you not get it. Still, there are loads of opportunities. Questions?
Would you like to ask questions?
Yes.
I'm just curious.
Sorry.
Oh yeah,
Go
no,
ahead. I don't want to repeat.
I'm just personally curious. You presumably heard like lots of chatter about like the level of the student stipend and things like that, and the 18,500. I'm curious. Would that put you off a PhD? This is deleted from the recording perhaps, but like so. No, I'm really curious because like a lot of the professors are involved also in lobbying, policy making, things like that. I'm really curious like your views on that, and also if I can be bold, including the 5 people online and the 17 people that were here, we have only 1 female, and I'm really curious. And that puts you on the spot usually, right? But do you know from your colleagues, like, is there something we're not picking up on about these barriers to entry?
Not just few
I hope if that's their choice. I'm just curious, you know. And what about the costs of being a future student? Yeah, go on, just shout out.
I think it would be cost benefit analysis. It would be more, despite the lack of money, it'd be more preferable than going into. It's probably not the wisest financial decision. Decided to move in finance jobs more, but have less fun.
Yeah, a PhD should be fun. It's probably accurate to say people don't choose it for financial reasons.
John,
I was just curious, guy. I was just curious. Thank you for indulging.
Maybe I just make a comment on that. In essence, there are statistics both from the Institute of Physics across the UK and Ireland and the American Physical Society, which reflect on where jobs use physics in their workplace. People with PhDs will have higher starting salaries and a longer career in those industries which use physics than the students who would have gone bachelors who have gone into those industries with bachelor's or master's degrees. So there is a benefit, at least in all of the physics-related industries. But that's not to say that in other industries you may have starting salaries in computer systems or Facebook or places like that, Google, where a lot of our PhD graduates end up, but you may be able to get into those from a bachelor's degree with some difficulty, but you may then enter and have 4 more earning years of power than you would otherwise have had during a PhD. But again, for students who graduate with PhDs in the STEM sector, where they then enter into either financial services or data science or those big internet sort of companies, they will often start at a higher salary than other bachelor's or master's entrants, and then be given more responsibilities very quickly. So I think a PhD is beneficial to you. It pretty much depends upon how you want to use it. But of course, I mean, if your ultimate goal is to be an academic researcher, it's the entry level for that. Okay.
So, John,
I'd say one, right? As someone living on the 18,500 at the moment for when I see that extra 500 euros. Not gonna lie, it'll be tough if you don't have a place in Dublin. I think I just have to say that straight out at the moment. Rent is extraordinarily high. If you're fortunate enough, like me, to have a secure place in Dublin that you can afford on your on the 18,500, it's going to be good. I know in our groups, a limited amount of remote work options are available, especially if you're more computational, theoretical. You won't have to be in college every day. If that's something more achievable for you, that you can live outside of Dublin, that's also positive. I know that's not possible for every group here. It's obviously, it's even not ideal for our group, even in my role as a kind of computational physicist. I still prefer to be in here having discussions with my supervisor, working things out on a whiteboard and working in the office, but I do a lot of work from home. It is tight, but there are opportunities, as Professor Zhang was saying. You know, you'll be taught for your supervision of the labs. I know a lot of PhD students pick up grinds. I myself teach at secondary school students maths on weekends. Particularly valuable. I'm interested in going into education and stuff after this. So it's an opportunity to pick up extra experience, but yeah, I'm not going to lie. 18,500 is not a lot of money that exists in the current world. And I don't know if it's going to get better or worse for that amount in the next few years. But it is a consideration you have to take into account as you go in. But as the others were saying, and even in our group, everyone who's done a PhD is no problem. In our, of all the ones I've known in Stefan's group before me, I'm sure the others can say the same. If they've left academia and gone on to work, they've no problem finding jobs, data analytics, software development, whatever you like, really. Yeah, but the money thing will be an issue for some people. Like I said, having accommodation in Dublin is the important part.
Thank you, John. So on the chat.
Yeah, so if I can comment on this, John just mentioned all the PhDs from Stefan's group have successfully graduated, regardless of the low stipend. They do survive, right? So don't take me wrong. The low stipend is really an issue. The school is aware of this, so our director of finance is there, right? So I'm your director of PG.
I'm not taking responsibility.
So what we are trying to say is the school is doing quite a lot, try to help the students here. So we just recently improved the stipend floor, so everyone will be guaranteed that amount of stipend. And I'm aware the college is trying to reform its scholarship structure, so they try to give people more means to survive, maybe in a relatively comfortable way. But my point is, it's terrible, but you can survive. And then you will on a good journey to learn much more, okay? And the important thing is you do enjoy what you are doing here. Research is very interesting, right?
I think the policy is changing. It's just a little bit laggy, right?
Yes.
I would be very surprised if it will change within these 4 years. Yes. Yes. It's coming.
So no better place for doing PhD. If you look up around the world, it's probably more or less the same situation. So in the US, it's not paid well. Yeah. So.
And as we are promised a massive global recession, 4-year security is not entirely bad. I think there's something on the chat.
Something on the chat. So right. Chances of being employed after your PhD, psychological questions. Most of the supervisor would guarantee certain positions, right? They recommend you to another groups if you really want to continue your research journey, like postdoc, right? So I know if you're doing nanoscience or photonics or microscopy, Intel Ireland would be an ideal employer for you. So we have lots of graduates are working there, earning much more than I do, right? So yes, it's a very good psychological question. So don't worry. I have never seen a graduate PhD who don't have a job.
But the difference is, if you go to Intel with a PhD,
Yeah.
you'll be going into management.
Yes.
Yes. Because after 4 years, you can project management, time management, resource management, write reports. So,
Yes, that's why they earn more than I do, right? Management. Anything from quantum science? Comments about future career?
There's loads of jobs coming up in the quantum area at the moment, very last year for quantum computation. Right?
Microsoft and IBM, some, yeah.
We have some collaborations here and picked up in some of those firms.
It's really hard. Students, my students have some jobs lined up before they, so they're fighting with knowing where they're going.
Professor Brandley, just a comment, her students have jobs lined up for them.
I'll add another comment. One of the things for PhDs, in your bias, if you're looking for jobs beyond year 4, the summer between years 3 and 4 is a fantastic time for like conference travel, international conference travel. So if you're wandering around the building talking to professors, ask them what are maybe the sort of conferences that you might be able to attend during those 4 years. A lot of people I know from my class, they find that their next position in that summer between years 3 and 4, for example. Well, Vladislav asked about being employed. We're all professors, but professor is a job title. Right? If we get sacked, we lose that. Doctor, you keep. Right? No one can ever take that away from you when you've finished, okay? So, you know.
The next title would be sir.
I think that can be taken away as well.
All right, any more questions? Please.
You guys mentioned that it'd be a nice idea to talk to professors, like, you know, just knocking door. Is that an acceptable thing? Just knock on somebody's office and say, hey, can I?
I mean, an email is good because some people are still working from home. Well, they might be teaching from before, but yeah. Because if you get this money, it's free money for the professor's team. So you are the valuable commodity in this equation again. Remember.
So the question is, can I just knock the professor's door? Is this polite thing to do? I guess the answer is yes. It's extremely polite to knock our doors. And also, Luis, just a comment, if you want to make sure there's someone answering your knocking, so email us first, okay? Right. Any questions?
Yeah, I want to ask about like the learning curve along the PhD, because I mean, you introduced very interesting topics, but maybe some of them like go too complex for us right now. Like, I don't know the background we really need to start, or how you can like, I don't know, learn along.
Sure. So the question is the learning curve. So how much effort we needed to put into the background research to get the PhD started? Is that the question? Comment.
Well, I would say that, you know, you're embarking on a journey of lifelong learning. And so you're even learning very much new things in year 4, which you are publishing or including in your thesis, that you had no conception of perhaps in year 1, or perhaps even your supervisor had no conception of in year 1. So you don't come, you're fully formed and an expert in your area at the end of your PhD, but that's clearly not the case at the beginning. So, you know, there is a trajectory that you will go through in terms of learning some of the background, learning some of the techniques, whether they're computational techniques or experimental techniques, or reading some of the literature, getting involved in the experiments or simulations of an ongoing student. You know, in my group, you would participate in beam times at synchrotron radiation sources, which are being led by a senior student, but you'd be there to do the night shift, perhaps. But you'd learn all sorts of different techniques along the way, and you'd be driving your own research program, which is for your PhD. So, you know, it doesn't come overnight. It doesn't come in 3 months and 6 months. It develops continuously throughout the first 2 years. And somewhere in year 2, hopefully you'll have published your first paper, or at least written it. And then it becomes much easier, should we say. But it never stops, in the sense that you will continually be at the coalface of finding out new gems of scientific knowledge and delivering them to the world.
So if you do pursue a PhD in the School of Physics, you will find that it's actually, the learning curve is quite gradual at the start. One of the nice things is that the school offers you, well, you have to do it. You set to taught modules or research modules in the first year. But you have a lot of flexibility about what you can choose. Your supervisor will often recommend you to do some. I took the ones offered by the School of Maths and High Performance Computing, which have stood to me for the whole time. But you'll actually find, for me, or at least for me anyway, the real learning curve is not necessarily about the material or the physics, but really about like self-management. This is a project on a scale like you've never undertaken before. It's 4 years. It seems like a long time when you're at the beginning of it. I can tell you now at the end, it's extremely short. You look back and you make sure it's like there are things I wish I could have redone differently in year 1, but there are things now I'm looking at. I'm planning out my time and making sure I can get everything done before the end. But yeah, the big learning curve will be managing this project yourself. As opposed to, don't worry about learning physics. You've gotten this far in your undergraduate degree. You'll be fine getting there in the PhD. But it's more so that kind of self-discipline and the management of your overall project will be the real test of whether you can get to the end of the PhD or not.
Okay, thanks. Thank you very much.